What I give you, planets or stars?
Other outside, the same one?
No. Oh, because it's another one in that series. They have, I gave my brother the planets one.
Right.
They, you know, stars one. I want you to check this. Now I'm getting the planets one. My brother be when he's done with it.
I would volunteer.
Okay, there we are. We are now live.
My early diagnosis.
Coming.
I know. She just like when I do 2 nights in a row.
Yeah, there's been a lot.
Well, I'm not gonna be here. I'm gonna be in Cayman, so I can't do
Oh,
that.
awesome. All right, well, we'll try and get involved. Maybe it's very bad. It's not so strong.
What he did last.
Hi.
Yep.
So I'm really having fun.
Good to call on you.
Sure. Sure. I'm just checking right now to see how many members we have.
Very good to check, yeah.
Yeah, I deposited.
Oh, excellent. Was it 2,500?
No, I wish it was starting, it was 2,000. Still good, right?
No, that's awesome. I'm gonna give them credit today. There you go.
205.
All right, everybody, you're on YouTube, so
Yeah,
say hi.
Rise reports.
Okay.
200.
Right up there.
Active.
You're probably not on camera.
That's amazing.
Yeah, we're, he's 12 away from our hiding.
We got 5 people watching already.
Great. So that's wonderful. It's on that little device. Everyone, of course, knows. So I'm going to grab a seat.
Okay.
So Lou, actually what I could use, are you able to get to this YouTube?
Oh, yeah? Yeah, let's.
Yeah, so monitor
Where's the
the,
camera? Is that where's the camera? Or it's not looking at me.
there's one camera right there,
Huh?
facing forward.
Oh, okay. So where should I go?
Well, I can switch to the other one when you're ready to start.
Okay. Should I use the mic or can you hear me?
As long as you stand near the computer.
Okay, I'll stand in there.
So where is it? Because I don't see a link.
You have the link in the email.
I don't have.
What is that?
It's what?
Or, you know what? I take it back. I do have personal.
What actually would like to hear from the city?
That's what I'm asking. Why don't you take a look and.
Well, it's on. Oh, yeah, I guess, yeah, then you.
Oh,
you can move it.
got you.
It's a channel.
Yeah.
I use my grandson, he said that's.
Cool. And then if there's any technical issues,
So September 25th.
that's it.
Here you go.
Turn the volume down.
Yeah, no, I'm not gonna monitor it.
But we need somebody to monitor.
Oh, okay, I guess I will monitor it. Okay.
Jeremy.
Yeah. I wasn't gonna say anything. What were the odds of it?
I'm sorry, I couldn't.
Somewhere between 0 and 1, yeah.
Just.
Yeah, I sent you that. I sent you that thing about from Bill Bryson's The Body. And
Yeah.
everything. Yeah. That's interesting. Maybe I'll update. Maybe I'll talk about it. Just start with it. 32.
Yeah, I'm muted, so. Should be fine.
Well, then someone told me as well.
We still got 5 minutes.
Certain way.
I have a fairly lengthy report before I kick it over to Jeff.
And where did that go? You're from North? I remember saying it.
We don't have any cover slides.
They showed me the Arkansas salt. It was partially.
Then you never change.
And it was that moment when there was a small.
Now what I can do is back to Zoom. Switch to this camera here.
Okay, so that's what they all see. Are we on, are we live on
Yep, we are live, so they can hear us on the internet right now.
yeah, look, just, I feel like I'm watching my father. That's really depressing.
All right, so everything that's up there is going to be shared.
Meaning I shouldn't block it.
Well, no, it doesn't matter.
Oh, that's the YouTube, so it's delayed anyway.
But blocking it only affects the people in the room right now. They see it directly.
Got it.
So on.
Oh, no, that's just shared.
This is
Okay,
what they see on
I
YouTube.
see. Oh, good. So I'm really tiny.
Yeah,
So good. That works. All right.
all right, so these are the slides you're gonna use.
I'm not using any slides.
All right,
I'll let Jenny use the slides.
I mean, if you don't want to use any slides, you can even stop the share, and then it just shows you.
Okay. I don't care.
There's the pointer.
I don't need a pointer.
That pointer.
I don't need no stinking pointer. We'll start in 2 minutes. We're starting in 2 minutes, YouTube audience.
2-minute warning.
2 minutes. Actually, for you guys, it'll sort of be 3 minutes because of the delay.
Yeah, that's, well, I didn't say this at all.
Phenomenal.
Yeah. I think that it is. Yes. I took 4 years. Your current CV said. So when I found like your weapon, we said. Yeah. That's a real. There's two, so the one that's active right now is the one I'm possibly.
So if I want to show the sun pattern, I need to bring it over.
Yeah, we can switch that.
With that. And I put it in here.
Yeah, I know. Yeah, that'll show the front.
So I should. Yeah.
Whichever one works better.
That's the map, yeah.
Yeah, I don't know. Really help me. So we try it. We'll figure it out.
All right, showtime. Thanks, everybody, and good to see everybody here. Appreciate it. I have somewhat of a lengthy report. I want to start with, it's all good news, I would say. I want to start with one of the things I'm most excited about, and that is the Astronomical Society has an award called the Mabel Stearns Award to the best newsletter. And we won, two of our editors, Tom Nolasco and George Caton, won third prize this year. We are very, very excited. I'm supposed to have, they should have won first. They should have won at least second, but Vinny the Thumbreaker was busy and I couldn't get him on. So that's the way it happens. But we may put him up to it again next year because the guy, when they called and said, we're going to give him third place, but you should definitely resubmit. It was a very tough pool this year, but the newsletters are amazing. And George, thank you so much. And Tom, thank you so much. There are upcoming star parties other than ours. I just want to announce briefly. The York County Star Party is at Susquehannock State Park, September 21st to the 25th. It's a really nice site, not too far away in Amish country. Basically, we take over a baseball field and the sight lines are pretty good. I would say it's very comparable, very favorably comparable with Blue Mountain Vista. Although there's no electric there, there is a pavilion nearby that you can recharge all your batteries during the day. I went to it last year. It was a lot of fun. There are hiking trails around there. There's stuff to do during the day. Really, really nice star party. So if you're looking for one more new moon before, just after the equinox, September 21st to 25th. Every year in December, the officers roll off and new officers roll on. We are very fortunate, and president and vice president and treasurer are term limited 3 years. So this is the end of my 3rd year, and that means somebody else needs to take over the role of president. Fortunately, we have Janet Rush, who's been a vice president, who's offered to step in. She needs to run for office, so you all have to vote for her. I know I'll be voting for her. But we also need a treasurer because Lewis needs to step off as treasurer, and we need another vice president. So, and there are also members at large positions and so forth. So if you have any interest, the treasurer's job, it sounds daunting, but really, if you're comfortable with QuickBooks, you'll be fine. You're really just depositing checks, you're balancing our checkbook, you're paying invoices, reimbursing members when necessary. One of the more tricky things is filing. We're a nonprofit and we have less than $25,000. So we file what's known as a 990 postcard with the IRS. And you got to know it's free, but there are a lot of companies that try and charge you for that. So you got to know which site to go to log into the free site so that you don't pay somebody to do what the government doesn't need you to pay for. You usually pay the insurance. We have insurance so that we have certificates of insurance so that we can do things like have star parties at Valley Forge, since they ask for certificates of insurance, not unreasonably. So it's more paperwork than anything. You don't have to know any constellations. You don't have to know any stars. You just have to be comfortable handling bookkeeping software, and it would really be appreciated. And it's a stepping stone to power. You become president after that if you're foolish enough to do that. Yeah. The vice president served in the absence of the president. I've been really grateful that Janet and others have stepped in for me. Friday nights are tough for me. I'm still practicing law full time, and I have a litigation practice. So a lot of times I don't have any control of my calendar. People who wear robes and slippers to work tell me where I need to be and when. So that's somewhat of a challenge.
You practice law. Have you gotten good at it?
No. 42 years and I'm still practicing. Yeah. So, and we also need an observing chair. Andrew has served us very well and very loyally for a while. He's been taking responsibility for the star parties, and he's been doing wonderful presentations at the meetings. I've taken a lot of notes at his meetings, and I was just at Cherry Springs a week and a half ago, and I had my notes from when he talked about objects in Cygnus and in Aquila, so for things to look for. So we need somebody like that. Yeah, I would recommend, if you want to be observing chair, you do know a little bit about the sky, at least know where it is. But we could really use some help there. And to make it easy for you, just email president@dvaa.org if you have the slightest interest. I'm going to reach out to people too. We haven't drafted anybody yet, but I wouldn't rule it out. The elections will be at the business meeting, which, by the way, will be December 11th at 2 o'clock. I don't know who the Eagles are playing, and unfortunately, because my December is so busy, I don't really care.
And that's a Sunday, I guess.
That's a Sunday, and I'm going to try and host that at my house. So, and unlike several prior meetings, we can have donuts. Unlike the Zoom meetings where we can't.
I have donuts. I don't know that it is.
Yeah. Another thing I want to talk about is we had a special board meeting a few weeks ago to deal with 2 telescopes that were donated to the club that we really couldn't use. One was a spectacular, an obsession scope, a very big scope that you basically would have needed 3 Sherpa to bring out for the club to use on a regular basis. And Barry Johnson arranged for the sale of both of these scopes, netted the club a cool $2,000. And Barry, I know that was a lot of time taken up. Well, I want to thank you for taking the responsibility for moving the scopes. Thank you very much. I appreciate that. We have The next two star parties, we've had some confusion because for a while we were making the cloud date the day before. And we had some discussion about it, and I've always thought that the day before cloud date was not the best plan. We tried it. We've had people show up on Saturday going, where were y'all? Now, sometimes people show up on Saturdays and there's clouds up there and you go, yeah, well, there's no stars. What did you expect to see? But so we've had to explain that through very nicely worded emails. Janet's been really good at writing those emails. But we're going to try and avoid that for the October and November, the last two star parties. So we're going to go back to a Sunday cloud day, cloud rain day, Saturday being the primary day. And we're making arrangements with the park and sending them an insurance certificate if they ask for it to do that, especially because the October and November are going to be a lot earlier in the day. So Friday would not be practical. Let's see, what else do I have to cover? I have two awards to give. Besides the Naval Stearns Award, the first one is the Night Sky Network Award to Janet Rush in recognition of exceptional outreach. Janet, would you come up so an appropriate photograph can be taken?
Thank you.
How do you want to do it? You're the boss. And there's it.
Oh, wow, thank you.
Suitable for Freddie. Yeah. One more. Okay.
Well,
You get
thank
to
you.
take
This
that
is
with you.
unexpected.
Thanks, Janet. And I have another one of these for award-winning editor, George Caton. Please come up. Here's your pin.
Oh, nice.
Yeah, and at least this one you got. Thanks. Thanks. Congrats. All right. All right, let's see. Did I cover everything? I did cover everything. So now we go to our reports, and Brian is not here to give the new members report, so I'm going to give that myself. And that is we have 4 new members this month, and we had a number last month. I don't have that list with me, but Christy Walsh, she here? How about Aditya Nathan? Don't call me, I'm in a meeting. Brody Carpenter and Stephen Crouchick. Well, that's 4 members. Hope to see you if you're out there. Hope to see you at a coming meeting. And we are up to 205 members, which is only 12 shy of our record of 217, which means we get to pay that much more to Muriel next year when the bill comes in.
Yes.
But that's all right. That's okay with me. So the next one to report is our treasurer, Lewis.
Well, he stole all my thunder. I was gonna say there were 205 people, but what I would like to talk about is actually, we take dues at the beginning of
Do you
the
mind
year.
standing in the front so they
Ah,
can?
Here,
Oh, I'm sorry.
because the people, they're already raising their hands on YouTube.
Exactly.
Who's talking? Where is he?
It's the good looking guy. So anyway, the idea is really, really simple. We always have memberships that are tuned at the beginning of the year. I feel bad in a way for people who register early and, they have to register again in January with high ice where people tend to send their registrations and where not. It's important. It helps us with our mission. Please register and re-register. We're going to send you out a ton of emails about it. Secondly, please kick me out of a job and replace me. It's not that hard. It is, I can truly say, I came to Philadelphia not knowing anyone. I joined the group. Within the year, I was secretary here. And that was one of the most valuable experiences of my life, period. It made me part of Philadelphia. It certainly made me part of this club. I unfortunately had to be a president at some point. Damn people. So,
It's picked off the internet, watch out.
yes, get us kicked. That was closed fist. That wasn't open fist. So, or maybe it was open fist when it shouldn't be closed. So anyway, it turns out that it sometimes seems daunting to do service for the club, but I find it's been incredibly important in my life. It has been rewarding. It's been a lot less grief than you'd ever imagine. And I recommend it to anyone. So thank you very much, and thank you, Internet.
Thanks. Janet,
Yes, sir.
outreach. Do you want me to move that so you can?
Yeah, we can, you know, the other end. You know, I like that.
Just like Ginger Rogers, you're going backwards.
And better than you going
Right,
forward.
exactly.
All right,
And sandals.
Did you want to show this first or the slides?
I think the slides.
Okay.
I guess that button doesn't work. I'll use this.
Gotta make this the active screen. Not doing that. That's interesting.
Yeah, we saw it before.
Yes. There we go. Okay. Let's click up there. Now it works.
No, I advance with the arrows. Oh, okay. All right. First thing I want to mention is we're having another observing clinic. We had one in August. It was lots of fun. We had a great turnout. But we didn't finish everything. We still need to have some more clinicking. So it turned out that Green Lane was a great site. So we're going to go back to Green Lane Park. If you haven't had a chance to see any of one of the club's favorite sites, come out and check it out. It's a good way to meet other new members and more expert people to get help with your scope. And we'll also do a laser pointer tour of the constellations and prepare for whatever is left of the observing season. So this one's pretty early because it gets dark quickly. So Saturday, October 15th at Green Lane Park, our backup weather date is October 16th, and it's open to DVAA members and immediate family. You do need to register. Click on the event and you can register.
Janet, where's Green Lane Park?
It's in Green Lane. It's where Lou lives. How do you describe it, Lou?
It's the corner of Route 21 Road.
Thanks.
You know where that is?
No, but I'll put it into my GPS.
Yeah.
It's
Western Montgomery County.
So
yeah, it's the northernmost corner of Montgomery. It's right where Montgomery County, Berks County, Bucks County.
so about how far from here in time?
45 minutes, depending on traffic.
Yeah. So one important thing to know about our website under observing is the link that's called observing sites, which show all the sites we regularly observe at, and has a map, how to get there, and has linked to Clear Sky Fox and things like that.
Right. And this event, if you click on the event itself, so when I say the event, you go to the website and there's a list of events. If you click on the Dark Sky Clinic, it will take you to all the details, including a map of how to get there, the link and the address to enter and the coordinates, whatever you need to know to get there. It's all on the link. So if there are any other people who would like to help staff the clinic, we already have about, I think, 5 people, but could you use a little more, a few more, especially folks that are familiar with go-to scopes, because we do have some people who need some help with that. So, but we'll have a great time. So I hope any of you who would like some help with your telescope will join us. Okay. Next thing I wanted to mention is Radnor's Fall Festival and Great Pumpkin Patch Festival. So many of you know that we have a good relationship with Radnor. They are so gracious to us to let us use this wonderful venue for our monthly meetings. And we try as much as we can to give back and encourage that partnership. So when they ask us to help out with an event, we try to do our best to comply with that. So the Fall Festival is Saturday, October 2nd, 1 to 4 p.m. at the Willows Park, which is in Radnor. I'm sorry, Sunday, yes. And the backup date is the following week. So Barry Johnson is, where's Barry? Yeah, raise your hand. He's leading the event. We have so far about 3 people. We have Barry and George and Mike Atwell are planning to come, and possibly Mitch. He's still on the fence. So if you do not have solar equipment, I wanted to challenge you to perhaps come anyway, and we'll lend you this thing called a sun spotter. And this is you can see a picture of my grandson here using it. It's super easy to use. Turn it around so everybody can see. All you need to do is stand so the sun enters here. You take this little pin and adjust the cradle so that yes, thank you. I would say. Yeah, so you move this so that the shadow disappears, and you take off the lens and you can see the sun right here. So it's super easy to use. I would lend it to anyone who'd like to try it for the solar observing. Just let me know after the meeting.
I can't. Did you buy that or make it?
I bought it, and I bought it for the eclipse. As you see, my grandson there is looking at the eclipse. And just a quick review of the upcoming outreach events, the fall harvest I told you about. Of course, we have a public star party October 8th. And Mike Tucker's going to be the one leading that. We have a star party at Upper Providence community in Anderson Farm Park. Al Lamperti is leading that. Anything to say? Do you need additional people or are you set? Right. We haven't been able to hold it. Yeah, other dates. Yeah. And finally, a community star party in Bluebell at Armand Trout Preserve on the 18th with 2 backup dates. That's all I have. But Al, did you want to mention the Youth Awards?
Yeah, you don't need to do anything.
Just stop the sharing here. That way you'll appear.
Okay. Last year, the DVA started a youth awards program. It's geared for middle school and high school students that have astronomy related projects. Many of the schools were not having science fairs because of COVID. So what we did, last week emailed 21 individuals, schools, or institutions, as well as a number of DVA members who have young folks who might be interested in doing astronomy related science projects. We came up with the idea of having 2 categories. One for individuals up to the 8th grade. We have first, second, and third prizes that are $250, $150. And then also a second category for high school students, again, doing astronomy related projects. Prizes there are $500, $200, and $100. So we hope that this coming school year, schools will be having science fairs, and the people in charge know about us now, and you will know about it. And when you go to DVA website, you see a little button on top that says Youth Awards. It tells you what the categories are, what the criteria are, and what to do for submissions. And we hope to have winners this coming year come to a meeting and present some of their work, maybe a poster session or something of that nature. So if you know of any individuals who are working on astronomy related projects, keep us in mind. You never know if they're going to win. Okay, thank you.
And Jeremy, the floor is yours. And nobody, there's no astrophotography. Although we're still having sessions, I know.
Yeah, the Wednesday prior to our regular meeting is the workshop, there's no on the calendar.
Thank you.
Nothing specific lined up for next month unless anyone wants something covered. Just send an email to astroimagers. DVAA.org. Or just show up.
Great. Thanks, Lou. We have rental scopes. I don't know what the status is right now. We were donated another refractor that Joe needs to look at and decide whether it's okay. But that was donated to the club. And with that, Jeremy, take it away.
All right, thanks, Harold. First, Lou, any questions coming in on YouTube or anything?
There are no questions coming in YouTube.
All right, everyone is silent. All right.
We're probably not as exciting as we can be, so pep it up.
All right, here we go. Let's get excited. All right, so for those of you who don't know me, I'm Jeremy Carlo, Programs Chair. So I'll start by giving you a little introduction of what's coming up the next couple of months. Our next meeting will be on October 14th, and that's actually going to be a special joint meeting between the Delaware Valley Amateur Astronomers and the Southeast Pennsylvania section of the American Association of Physics Teachers. So we're actually going to have a bunch of physics teachers at the high school and college level who are going to be joining us. So I think that'll be a great venue also to talk about the youth awards, because we may have some teachers who may be mentoring students, who may be interested in getting involved. And our speaker will be Professor Joey Nielsen of Villanova University. He was on the team that recently imaged the black hole at the center of the Milky Way. So we'll be hearing about that. On November 11th, we're going to have Rick Schwartz, who's a DVAA member and who's actually here tonight. Did you want to give a quick plug for your talk? Yeah, come on up.
I'm going to be talking about my involvement in the Transiting Exoplanet Survey Satellite Mission. I've done over 1,400 observations using 2 and 1 meter telescopes around the world and have discovered about 200 exoplanets. So I'll have a lot of good information, scientific findings to share. Looking forward to it.
All right. That's good, because my notes just said exoplanet research, so that makes it sound a lot better. Yeah. All right, so that's what I have scheduled so far. Tonight, we're very happy to have Professor Dave Goldberg from Drexel University. He's a professor of physics there. He's the former associate dean of graduate studies. He said he stepped down from that and returned to the real world, but he is currently the associate head of undergraduate studies. Dave got his PhD at Princeton University. He did his undergrad at Boston University, including minors in math and religion, which is kind of an interesting combination. He has a number of awards and grants. His research interests include gravitational lensing and the physics of the early universe and how those relate to one another. He's written 5 books or book chapters. Is that up to date?
Well, one of them is a fun ghostwriting that I'll be happy to discuss after the fact.
Okay, and he's also the author of a number of popular articles in magazines and newspapers. So please join me in welcoming Dave Goldberg to the DVAA. Is there a way to get a full screen on this?
So I think you just go to, in Google, you're there, slideshow.
Just want to share screen, share that.
And here,
Where do we go on this?
slideshow.
There you go. Here's your clicker.
We just, I don't have permission. Oh, that's concerning. Well, well, we could have requested. Well, we'll request when the time comes if need be. Thank you so much for having me. This is I'm sure you hear this from a number of your speakers. This is my first in-person talk since the before times. I mean, not counting my own students. Speaking of which, George came up to me beforehand. I had not seen him in 9 years since I had him for a class, or vice versa. But so it was very exciting, and it's exciting to be with you tonight. One of the things I think that's interesting, like when you're talking to an astronomical society, is in some sense, you guys have heard a lot of these sorts of things before. So I decided tonight in my discussion of gravitational lensing and gravity in particular, to sort of talk about things a little bit differently. So, just to be clear, for those of you who are anticipating things to come, I'm going to mention the 1919 Eddington eclipse and all of that history that some of you may have already heard of. And if you haven't, then that'll be very exciting. But I'm also going to talk about like how gravity works, and perhaps my least favorite analogy for how gravity works, which is the whole rubber sheet and a ball and the bending. And you've seen this before, and I'm going to show it to you, and then I'm going to complain about it for a little while and tell you how we can do a little bit better. But all of that is going to be setting the scene to describe gravitational lensing. And you can see in the background this beautiful field and all of these galaxies. And my apologies to the folks online. I suspect that a camera on there is not going to quite do the trick to catch all of these. But you can see, if I can make the laser work, you can see all of these extended all of these lengthy galaxies, especially things like this, that the image is stretched out by gravity. And we're going to talk about how that works. I got a couple of equations that are going to show up. They're going to be pretty straightforward. Feel like you're up to it. If not, you can take me out back afterwards. All right. Okay. So the basic plan of attack here is we're going to talk a fair amount about how gravity works, how gravity itself works, sort of some fundamentals, a little bit of history. History at sort of the physics professor level, not the historian level. So there's gonna be a lot of hand waving about what Galileo did or Newton did, but I don't know how much will hold the scrutiny. There's gonna be a couple of asterisks in there as well. Those are gonna be things where so-and-so discovered something, but in point of fact, they didn't, right? There's the popular version of history, and then there's what was actually shown. We're going to talk about what gravitational lensing is, how it works, how it manifests itself. Then I'm going to show you some cool pictures, but more importantly, we're going to talk about what they actually mean, what we can learn about in terms of the physical universe, and just a little vocab in terms of gravitational effects. And then I'm going to tell you about some things that I'm working on, both lensing related and not lensing related. I will give a spoiler. I have a new book coming out. This was, I guess, number 5. This is is a textbook on special relativity called "You Are the First Audience to Hear This." I'm not still thrilled about the title. A relatively painless guide to special relativity. Which, as a textbook, you're a professor. Would you adopt it or not? I don't know. Unfortunately, I contacted my editor, and the cover isn't ready yet, so you won't get to be the first to see what it looks like. But then again, neither am I. So, I want to prime you for what an amazing effect gravitational lensing is by just showing you. This is a Hubble image, and you can see. Try not to get my hands confused here. You can see 4 different blobs here. Those are the same object. This is not a telescope effect. This is a purely gravitational effect where we're able to observe things like this fairly regularly. And what is happening is that those things are being distorted by this object. And geometrically, the idea, I think that's a smart move. There's going to be a fair amount of contrast here, so you don't get to see my beautiful face online as well, but you will get to see my slides a little bit better. geometrically, what's happening is this object in the center is closer to us than a quasar in the background. And as the light comes toward us, it's getting bent, and we'll talk about how it gets bent and how it shows up in our telescopes, your telescopes. So I want to start off, as I said, with a little bit of history. So Kepler's laws, 1619, maybe you know the history a little bit. You had Tycho Brahe, his boss, very rich, saved the king, or the king's son, or something like this, had this giant island spanning observatory, actually had a couple of them. This was before telescopes were in broad use, and was taking all of these observations of the planets, and in particular the planet Mars. This is Kepler's drawings here. And Kepler discovered something interesting. I mean, these observations were taken in 1619. I believe Brahe died 1610. You may know the popular story where, you know, he was poisoned, perhaps. You know, he had a lot going on, you know, so had a drunk elk and had his nose chopped off. I mean, Brahe was an interesting guy, not least of which was because posthumously, that guy, Kepler, stole all of his notes in order to form his theory about how planets worked. And so Kepler's laws were fairly straightforward. Planets moved, and this is the most important one for the purpose of what we're going to talk about tonight. Planets move in closed elliptical orbits. The closed is my part, but that was something that he saw observationally, that Mars and the other planets moved around with elliptical orbits, and I've left off the part with the sun at one focus. There's another, just for completeness, planets trace out equal areas in equal time. So when they're closer to the sun, they go faster. When they're further, they go slower. And then there's this period squared equals distance cubed, which basically just tells you how long a year is for any given planet. And the further out from the sun it is, the longer the year is. Now, I should note, by the way, that I've wasted one of my equations because we're not going to use this one at all. I just wanted to make sure that I'm not going to give you a list of 3 and say, well, here's the first 2, and there's also another one. So Kepler's laws, this is just sort of the context here. We're, 400 years old at this point. But in trying to understand how it worked, Newton, all of this was known observationally. Newton in 1687 was basically able to develop in his Principia Mathematica the laws of gravity as they were. And the history, the history of all of this was that Halley and Wren and Bacon, I believe, were arguing about what the form of gravity needed to be. And one of them basically asserted, oh yes, there must be an inverse square law. I have a proof here somewhere. Was unable to provide it because it's actually non-trivial to do it, and without Newton's calculus, pretty much impossible. Went down to Newton. Newton was able to basically develop all of this by developing physics and mathematics as we know it. And he found that gravity obeys an inverse square law. And just to be clear about what that means, right? Because this is sort of an important point in talking about how gravity works. The idea is you take two stars or 2 planets and you double the distance, and the strength of gravity goes down by a factor of 4. That's my second equation. This is there's a lot that this tells you about the nature of the universe, about the nature of gravity, and how things actually work. It's a strange equation in a lot of ways, and the theory itself was incredibly successful, but upon additional reflection, it's kind of strange. Like, why should it be that the strength of gravity between planets goes as an inverse square law and not 1 over r cubed or 1 over r to the 4th or some other some other formula entirely. And what's more is if I move this planet around, you know, if I've got some superpower and I can just pick up a planet and shake it, will this gravity instantaneously feel the change of gravity? Newton's law basically, Newton's theory of gravity basically said, yeah, you'll see it right away. There's no propagation of gravitation through the universe. And according to Newton, the law is exactly 1 over r cubed, 1 over r squared. Now, there's a reason for this. And what I would like to do is to sort of give you a sense of like the next level of sophistication. So, you know, 5 minutes in or whatever, we're already trying to be a little bit more sophisticated than Isaac Newton, which I recognize may be a mistake. But there's an idea that we get in the 20th century, and this actually postdates Einstein, but does give us a very good sense of how this works, which is how the other forces all work. So when we have things like electricity, for example, if I have an electrically charged particle over here, and I have an electrically charged particle over here, and I move this one around, the signal goes from here to here via particle. And that particle, you know, we draw these little fancy diagrams, they're called Feynman diagrams, but they just basically mean you have an electron and an electron. They send photons to each other. But what's more is the further you are sending those photons, the more spread out they get. This is a big deal because if you remember your high school geometry, you'll remember that the surface of a sphere goes as 4 pi r squared, that's the r squared. You live in a 3-dimensional universe. You've got a sphere. The surface area of a sphere goes as r squared, and that's how gravity works. 1 over r squared. But you can actually generalize this. You can start imagining what it would be like to live in a universe with different numbers of dimensions. I know this is not exactly how you thought this talk was going to start. That's okay. Bear with me for just a minute. Just out of curiosity, though, how many of you are familiar with that book, Flatland, by Howard? Many of you, not all.
Great.
It's a great book in a lot of ways. Super sexist, though. Really, like there's certain things that are definitely of its time that don't necessarily hold up. But the idea is that you can project yourself into the view of how it might look to live in a universe with different dimensionality. And universes of lower dimensionality, 2-dimensional universes, Flatland, or 1-dimensional universes like a line land, those are almost ridiculously simple. But by the same token, we can imagine living in a 4-dimensional universe or a 5-dimensional universe or a 6-dimensional universe. And the cool thing about it is, without knowing anything more than what we just told you, this idea that particles will attract or repel depending on the nature of force by sending out signals, if you tell me the dimensionality of the universe, I'll tell you how the force law will go. 3-dimensional universe, 1 over r squared. 4-dimensional universe, 1 over r cubed. 5-dimensional and so on. Turns out, by the way, that for anything larger than 4, you basically don't get stable orbits at all. Like you don't get planets, you don't get planetary orbits, you don't get even electronic orbits. So there's a reason we live in 3 dimensions. But that's all well and good for these sorts of things. There's something that's special. There's something that's special about the universe that we live in. I mentioned Kepler's discovery early on. Kepler's discovery basically said, observationally, and then Newton proved mathematically, that planets move around in these closed elliptical orbits. They infinitely repeat one another again and again and again. And that is an exact solution to Newton. What I've drawn here is a different force law. And you might think this is kind of a ridiculous force law. This is 2.9 dimensional space, right? I already told you how it works. It means that the force law goes as 1/r⁴ a weird sort of equation. All it means is just a little bit different. And you're like, dude, why would you ever plot something like that? Because this is almost exactly how it works for the planet Mercury. So one of the things that we realize, we measure this observationally, and it's an incredibly difficult observation to do, but that Mercury does not have a perfectly repeating orbit. Mercury's orbit precesses. It makes a pattern very similar to the one I've drawn here, which I've sort of exaggerated for effect so you can see it, but so that as it moves around, its point of closest approach, its perihelion, changes cycle by cycle, year by year. Now, Mercury is incredibly complex because it's got a bunch of effects going on. One is the biggest effect by far actually has to do with Jupiter messing it up. But even if you've subtracted that thing off, Mercury's perihelion moves by a small but measurable amount of about 47 seconds of arc per century. Extra. Didn't understand it. Is totally inconsistent with what Newton described, and even our basic understanding of how it should work when you send a signal from the sun to Mercury, right? It should drop off as 1/r², and instead it drops off as 1 over some other power. So Newton was mostly good enough, but wrong. Okay. This was one of the big tests of what will become general relativity, but not necessarily the one that we want to focus on today. So how does it really work? Okay. So you've probably seen some variant of this quote before. This is John Archibald Wheeler. Space-time tells matter how to move, matter tells space how to curve. And you may have even seen this sort of image before, where the idea of gravity in Einstein's universe is you've got some big, massive object that deforms space by bending it downward. Seen some variant of this before? And you can go to the Franklin Institute, you can do a little demo or something like that with a conical, a penny that sort of looks like it's going in an orbit. And it looks great, until you're there with a kid who's like, yeah, but why is it bend downward? And you can't say due to gravity, because the whole point is we're supposed to be describing gravity. This is a visual aid, but it's a very incomplete visual aid. And it doesn't actually really tell you how to compute anything about the universe. So I want to tell you a little bit, because I want to give you a sense of how things work and why we get this sort of effect, and why it's a little bit difficult to draw. And I don't really blame the artists for doing these sorts of diagrams, these sorts of pictures. So this is an experiment. This is 1959, the Pound-Rebka experiment. Obviously, again, this postdates Einstein's calculation, but we knew that this should happen. You can take a laser or any other signal from even the ground floor of a modestly tall building, not very, and shoot it upwards, and that light will lose energy. We can see this, by the way, we see the same effect coming off of white dwarfs. So white dwarfs have a much stronger gravitational field than the Earth. And we look at the light coming all the way to the Earth, and the light loses energy. Or you can do this again on the Earth. And just to give you an idea of the magnitude of the effect, if you compare the surface of the Earth to outer space, the effect is about 1 part in a billion. So it's a very small, but potentially measurable effect. But there's an implication to it. Light has a frequency. And that frequency you can think of as a clock. And so the idea is, if I imagine that these are ticks of a clock as the light is coming off the surface of the Earth, the argument is that what these people on the surface, this is the Earth, is supposed to be a star, but what these people on the surface are measuring is measured as slower far away. This is one of the most important predictions of relativity. And by the way, I mean, in order to make GPS devices and things like that work, this has to be true. Otherwise, they'd be off by significant amounts. Time runs slower near massive bodies than far away. Now, I should say, again, this is a prediction of the theory. This is what we mean by space-time being curved, but it's a small effect in human life. 1 part in a billion on the surface of the Earth compared to far away. You may have seen in science fiction. Oh, what was that? There was that movie, you know, where they go to a planet and age very, very slowly compared to far away. If you go to a very massive star and go to the surface, you might age much slower than far away. If you go to the surface of a black hole, you age not at all compared to far away, but you do have the problem that, you know, the gravity on your feet is going to be much, much larger than the gravity on your head, and you're going to be stretched into spaghetti, an effect that is popularly known as spaghettification. You'll die, but for what it's worth, you will die young. So this is one physical effect that we care about. There's another physical effect that Einstein showed in 1905 in his special theory of relativity, and that's that things that are moving fast also have their clocks run slow. So this is a prediction of special relativity, and one of the best effects of this is that, for example, if you have cosmic rays coming down from the sky, they should decay very, very quickly. None of them should make it to the surface of the Earth, but we are able to measure them on the surface of the Earth regardless, because their internal clocks are running slowly. So just to remind you, being near the surface of the Earth, your clock runs slow. Going fast, your clock runs slow. 2 basic effects. Now, out of curiosity, how many of you had to take some sort of like intro physics back in the day? Many of you, not all. And you did probably a fair amount of projectile motion, things where you had to do this, right? You're like, you throw a ball at 5 meters per second at 30 degrees from the horizontal, and so on and so forth. And you go and you compute that projection of the ball because you use Newton's laws of gravity to do it. But we just said that Newton was wrong. So I want to give you just a sense of what Einstein actually says about this. Einstein basically says, no. The real way that things work is that by and large, particles are lazy. They want to get places as quickly as possible, all things being held equal. And the problem is, if you go and take that route between point A and point B, well, that route keeps you too close to the Earth and time runs too slow close to the Earth. If you take that route's very long. And so in order to traverse it, you have to travel real fast, and then your clock also runs too slow. That's the Goldilocks one. That one's just right. And I can sort of assure you, there's no whiteboard here, so we saved that. I can sort of assure you, you get the exact same result under sort of weak gravity conditions that you get when you put in Newton's laws. Except it's a totally different principle. Okay. That's a ball going in a parabola. What about light? This is a little bit more up your alley, right? Because this is exactly the sort of thing you're thinking about when you have lenses and telescopes, right? How does light travel through a physical lens? There's this angle of, there's this Snell's law, N1 sine theta, that you may have seen. But I can ask it in a somewhat different way. What is the root, unfortunately, I have to point with my finger at this point because I seem to have abused the laser pointer to a degree.
To use the mouse cursor too,
Oh, that may be beyond my capabilities. Where's the mouse cursor?
just use the trackpad.
Oh, well, yes, that works. So if you were going from point A to point B, if a light beam was going from point A to point B, what's the path that it will take? And in this particular case, the idea is that on the left, you might have air or a vacuum, and on the right, you might have glass. And light will take the path from point A to point B that minimizes the amount of time. And if you're having trouble picturing it, you can picture it like this. Suppose you're a lifeguard on the beach, and point A is your lifeguard station. Point B is a person drowning in the water, and you want to go save them as quickly as possible. Same basic principle we're talking about with the particle. How do you get to them? Well, if you go to a straight line, you're going to be on the beach for way too long. Hero. Thank you. If you go in a straight line, you're going to be swimming through this water for way too long. And the water is slow. You're slow in the water. I mean, I don't know about you, but I certainly can run on a beach much faster than I could swim through the water. And so you won't get to the person until longer. Better to go almost parallel to where they are on the beach and then swim a sort of minimal distance. And Fermat, the famous Fermat's last theorem, Fermat, same guy, basically showed you get the exact same solution. That there's this principle that you can figure out what path light will take by just assuming that it's super lazy and wants to get there in the minimum amount of time. And as I say, this is exactly the way that ordinary glass lenses work and predict all of it based on that. So, same basic idea with light from astrophysical sources. If you imagine this is a star, you imagine this is the Earth, and we ask, what path will light take from the star to the Earth if this is some sort of massive body? Well, this light has you going past a galaxy. That galaxy has a big gravitational field. Near that gravitational field, time runs kind of slow. Because time runs kind of slow, even though this path is direct, it's kind of slow. You can avoid the gravitational field almost completely by going like that, but guess what? That's a geometrically very long path. That's not such a great option either. But instead, this path is just right. And so what happens is light is bent around massive bodies. You can even, if you work out the details, find a very interesting result of this. I brought this entirely for this purpose. Here is a hemisphere of glass. And the idea is if you basically took a massive body where the thickness of the lens basically tells you about the projected mass of the object, you will get exactly the same solution. So if you'd like to know how light would be distorted by a massive source of this basic shape, you just have to look through it. And one of the things you'll know if you look through a lens like this happens to be useful for magnifying maps and things like that, is it depends very sensitively how the objects behind it actually appear, depend very sensitively on the object, depends where your eye is. You know there's a focal point or a focal plane. And so we care about the geometry of the Earth lens and source system, and that tells you quite a lot. The other thing we see from this pretty much immediately is that the amount of bending is going to be, in some sense, a measure of how massive the body in between is. So this is a more general version of this cartoon, right? Here's the massive body. This has been used in newspapers and so on. Here's some astrophysical source, and these light beams get bent. You can even get, as I say, more than one solution to this. You can get multiple images because both of these are paths such that if you moved that path ever so slightly, it would be a longer path time-wise. And so because of that, they're all local minima. And you can get multiple images of the same object. So how could we actually determine whether this was true, whether this was the right way to describe the universe? A solar eclipse is sort of the ultimate physical scenario to make this the case. In 1911, Einstein came up with an early draft of his theory. And then in 1914, there was an eclipse in the Crimea. This would be perfect, a perfect opportunity to measure Einstein's theory. And there's a reason you haven't heard of that eclipse, or probably haven't heard of that eclipse. 1914 was not the best time to be observing in Crimea. World War I, the equipment got confiscated, it was cloudy weather. All of these things basically prevented anybody from going and trying to observe whether or not a star would be deflected. Now, the plan here, just to be clear, because we're gonna actually do this, is we have photographic plates. We can see where stars actually are on the sky. The sun is the massive body. It can deflect the position of a star as it would appear. For what it's worth, it's going to make the stars appear further outwards, away from the sun than they normally would. The problem is, if the configuration is Earth, Sun, Star, normally you can't see that. And you can't see that because, you don't see stars during the day, except during an eclipse. So, we weren't able to observe it in 1914. And that's a good thing because Einstein screwed up. He was wrong by about a factor of 2 from the calculation, and there's a reason why. So, I want to just say a little bit about how time and space work, right? You are moving through time, you are moving through space. You are moving through time at 1 second per second. But you are moving it through space much, much slower than that. To put things in the proper units, it would be light units. So for example, the Earth, as it goes around the sun relatively quickly, 30,000 meters a second, takes 1 year in time to go around the sun. Travels 1 year into the future. On the other hand, the distance it travels, well, we could talk about that in meters, but those aren't comparable. To compare, we need to talk about things like light seconds, light minutes, light years. And that's the distance that light travels, for example, in a minute or a second or in a year. So in 1 year of time, we only travel 50 minutes in space. You are, for all intents and purposes, sitting still. Light, on the other hand, travels at 1 light second per second. It travels through time, it travels through space, and it travels through them at the exact same rate. And because Einstein's original calculation in 1911 basically only included the time part, but didn't include the space part, he was wrong by a factor of 2. If we'd measured it in the 1914 eclipse, Einstein would have been embarrassed. The theory would have taken a big hit, and it's not clear that we would have gotten general relativity when we did. He fixed it by 1915, and he published a final version. And then in 1919, we had this great scientific victory when Eddington, a British scientist, confirms Einstein's theory that a star, which was lensed by the sun, was 1.75 arc seconds from where it was supposed to be. Hooray. Except for one thing. I put a little asterisk there. I warned you I was going to do this because, given the actual error bars on his measurement, it was actually consistent with Einstein being wrong as well. I mean, it's been confirmed many times since then, but almost every description of this always says Eddington confirmed Einstein's theory. But the reality is, had Einstein been wrong, Eddington's results would not necessarily have said that. Nevertheless, we have been able to measure gravitational lensing in a huge number of circumstances. So, for example, we live in a very dynamic place. The stars in the galaxy are moving around. There are potential lumps of interesting things in the galaxy, stars. There's potential for things called machos, which are just a really tortured acronym for massive compact halo object. And one of the things that you can do is you can wait for some massive object to pass in front of a star. And when it does, the gravitational field basically temporarily increases the brightness and then decreases it again. It gives a sort of characteristic curve called a microlensing curve. And we can see these things fairly regularly. And from that, you can sort of tell what the mass of the thing doing the lensing is. And occasionally, you get these little secondary results. Like if the thing doing the lensing has a planet, for example, you get to see the lensing from the star and you get to see the lensing from the planet. And you're seeing it only in gravity. You're seeing it because it makes something behind it brighter. Now, here's another kind. So this is a little cartoon, but I actually tried to make it reasonably accurate. Here's the, this is the perspective of a massive object. Here's just a bunch of individual points that are meant to represent different markings on a galaxy of where they would be if there was no gravitational lensing. But as I say, gravitational lensing sort of pushes things outward from where they would be. And so what you see is, because of lensing, this little cross gets stretched out vertically. This is actually a pretty generic effect. We call it shear. And the idea is that you get galaxies. So remember, you're there, the lens is here, the galaxies are here, further away. When you see them, they get stretched out, and they get stretched out in a way that is perpendicular to the separation from the center of the lens. This is a very rich cluster, very well studied. This is Hubble image of Abel 1689. I think the folks in the room are going to have a little bit more luck seeing some of these things, but you can see these very bright objects. Those are members of the cluster. This is a rich cluster. Those are the things that are doing the lensing. But then you can see a lot of little individual background galaxies, some very faint. This is one right here. Take a little looking to see. There are literally hundreds in this picture. Here's one, here's one, here's one, and so on. But let's just look at this one for a moment. And what you'll notice is that they're aligned in such a way that they are perpendicular to the center. And in fact, if you take their orientations and sort of add them up and average them, you get an image very much like what you get here. Perpendicular, 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 perpendicular. And you can use this to weigh the cluster, to figure out where the mass is without having to say there is a star and so I assume it has mass. Instead, we're able to basically take these distortions, add them together, and figure out where the stuff must be. It'd be as if I gave you an image through a magnifying glass that was all distorted, and you'd say, oh, I can figure out where the glass is. It's the exact same idea. Now, this is important because you may have heard that most of our universe is invisible with something called dark matter. And so we can't see it in X-ray or visible or any other form of light, but this allows us to basically measure its gravitational effects regardless. This is an example of weak lensing. This is a very famous example from a while ago now, but still, I think, a very compelling one. It takes a little doing to explain what this is. You can sort of see the optical parts of this by looking at the individual galaxies here. You can see them in whitish. But what the system is these two very big clusters of galaxies that have recently, millions of years ago, passed through one another. This red represents X-ray, And you'll notice there's something that looks very much like a shock wave here, because it is. And so what's happened is when these things do pass through one another, the gas got stripped off basically of the galaxies and sort of is trailing behind. So, this guy used to be over here and is flying that way. This guy used to be over here and is flying that way. And the gas got ripped off. Now, if you didn't know any better, you could calculate all of the mass in a galaxy with stuff we know, with what we call baryonic matter. And you would say, oh, it's a little bit stars, it's mostly gas. And so you would assume that this red, where all the gas is, should also be where all the mass is, handy mnemonic. But it's not. Because we can do this exact same thing by looking at these background galaxies, reconstructing the mass, and that's where the blue is. The blue is basically just meant to be an illustration of where the mass measurement is. Whatever it is, it passed through without ever caring or noticing. It's dark matter. Dark matter does not interact with itself. And this is one of the great tests that dark matter is a real thing. There are other sort of fun ones. I'd be remiss if I didn't at least show you some other possible cool configurations. Sometimes you get very, very lucky and you get a galaxy and you get sort of a background quasar, a bright object. And if they're exactly lined up, just like if you exactly line up something in a scope, you can get a ring, what's called an Einstein ring, where basically this is a single, what would normally be relatively ordinary looking dot-like thing that has been distorted into the shape of a ring. And in principle, if you wanted to, you can go through and you can estimate the mass of the lensing galaxy. One other sort of interesting version of this I wanted to mention, but it requires me to just tell you one more fact about the universe, and that's that the universe is expanding. This is a great discovery of Edwin Hubble, 29, excuse me. People like showing this chart, but of course the experts in the field will know that Hubble was, it was a great discovery, but the details are wrong by about a factor of 8. But the universe is expanding, which means that galaxies that are far from us are getting further faster, and galaxies that are closer getting further slower. Another sort of terrible analogy of how the universe actually works. We sort of imagine galaxies painted onto a balloon that we're inflating. The thing is, this magic number H0, the so-called Hubble constant, this number tells us almost everything. It tells us about how quickly the universe is expanding. And so from that, if you think about it, saying how fast the universe is expanding, it also gives us a time scale of how long ago it was when the universe was a point, how long ago the Big Bang was. This is the magic number that tells us the age of the universe. Very important number in cosmology. But in order to measure it, we basically need to know, we can measure how fast galaxies are receding, we need to know how far away they are. So here's sort of a fun experiment. So imagine you have a quasar. For those of you who think quasars are very exotic, you could replace the word quasar with light bulb. And it's far away. Here's some galaxy. You can get multiple images of the quasar. Here's the image of this. There are two of these. You can draw these curves. And now imagine that quasar flickers. Now you can sort of do an estimate of how this would work just by looking at this diagram. This path, this upper path, is shorter than this lower path, which means you're going to see this version, the top version, flicker first, and sometime later you're going to see this bottom version flicker. These have an offset that have been corrected by about 520 days or something like that. Year and a half. Same objects, just offset from one another, flickering. And so what we know is that, in words, this path is 520 light days longer than the other one. And so what we can do is if I know what the difference between this length and this length are, I can basically say, oh yeah, that gives me an absolute scale that tells me how large the whole thing is, which also tells me how far away that galaxy or cluster in this case is. And so it gives us the scale of the universe from one system, just from one flickering light bulb. Just kind of amazing. I want to just spend just a minute or two just telling you, how my work goes into all of this. I mean, when we're talking about all the distortions of shapes and light and things like that, and the stuff that I'm working on tends to sort of think about how things work, not just in terms of stretching out galaxies, but in terms of making these sort of banana-like shapes, such as you see here. And I just want to mention a few of my students. My former student, Justin Bird, made this wonderful pipeline that sort of allowed you to analyze these things. And we mapped out the cluster Abel 2744 using this. And it's basically the same sort of approach. You go through, you measure all the distortions in the individual galaxies, the banananess in this case, and we figure out where the stuff is and how much of it there is. A really interesting one that I'm currently working on, you'll notice the date here, we just published this with my student Evan Arena and our British colleague David Bacon. It basically involves trying to figure out like the statistics of the masses in the universe by noticing the distortions of two galaxies that appear near one another and basically comparing how much both of them are distorted by this gravitational lensing effect. One thing, and this may be oh no, this one is working. One thing that we are very excited about is the ability of the Webb telescope to basically give us like unprecedented resolution and look at some of these systems in a way that we weren't able to before. So what I've got flashing here is the same cluster shown with Hubble and then JWST, Hubble and JWST. Just to give you a visible sense of the difference. And if you look carefully, especially at the JWST, you can see some of these lensed galaxies pretty clearly, even just by eye, even without an algorithm. This was the one that unfortunately doesn't matter. It's not an amazing. I mean, I could try. I could, but I don't have it viewed up here, so don't worry about it. It's just flopping it around. One of the things that's very interesting is when you study how images of galaxies get distorted, you start thinking about a lot of related problems. And my colleague Rich Gott at Princeton and I have thought a lot about this in terms of analyzing the quality of map projections. And so recently, in sort of goofing around, we came up with a series of double-sided maps that had sort of minimally distort the shapes of continents and boundaries and things like that. And I'm a little embarrassed, but also kind of proud. I don't know how to describe that feeling. Time magazine listed it as one of the best inventions of 2021. So you can, if you want, you can read about the details of this and other related maps at this paper. And then finally, I just wanted to mention that I've talked about and thought about some of these things at various levels of sophistication. My first book was A User's Guide to the Universe, which is very fun. I wrote with a graduate student in my department about a dozen years ago at this point, in which we sort of answer your sort of cocktail party questions. This was my second book. It was all about symmetries. This is a textbook. This has the most equations. I don't need to qualify it any more than just saying it has the most equations compared to anything you'd like. And this one's coming soon. It was based on a special relativity course that I taught actually during pandemic, where we realized, oof, the standard textbook, not so good. And so basically based on feedback from the students, we started talking about what would be of interest to them. And we developed a framework, and I turned those lecture notes into a relatively painless guide to special relativity, which is going to be published by the University of Chicago Press next year, and which I'd hoped to have a cover for to show you, but I don't. thank you so much for having me. I am very open to whatever questions you have about this or any closely related phenomenon. So,
Hey, for starters, I have used Stride to the universe.
no. Okay, hi.
No, for starters, I have a user's guide to the universe, and it came to me from a relatively rare and interesting path because my mother gave it to me. So, not the most astronomical minded woman, but she heard of it. So anyway, I have a question. I'm not even quite sure to how to ask it, and so hopefully you help me.
I bet this room full of people could help us.
So I imagine that just because there's all sorts of lensing events, obviously we only see things that appear to be things into our view. I mean, if things were not in our view, they would be not lens or maybe micro lens or so. Do you have any sense of the things that we look at that are significantly lensed as a percentage of all the possible things we could look at? It seems rare on one hand, but it doesn't seem rare on the other, right?
So that is a just whoever's were you the one monitoring YouTube in case because I want to make sure they could hear the question.
Yes, so I am monitoring YouTube
And
although
they
my
can- and
battery
they
is
can hear
running
you.
low, and unfortunately, no one has asked a question, even though.
No, but I wanted to make sure they could hear you. So,
Okay.
okay. But I'll repeat it anyway, which is the question is lensing seems like you sort of have to get lucky because here's the lens, here's the source, they more or less have to line up. We do have some, it's a numbers game, right? So part of it is space is big. There's this idea of the cosmological principle, which basically says that on the whole, the universe is homogeneous and isotropic, which means that you're getting sort of a random sample of the universe, right? And so we can do things like calculate how many strong lensing effects, because that is a thing we can talk about. Like when you get multiple images, how many strong lensing objects we should get. And we could sort of reverse engineer it because we could say, if for example, the masses of things were very low, we wouldn't see a lot of strong lensing sources, strong lensing systems. Because we see a certain number, you can go and basically estimate masses are high, these are the probabilities and so on. Are there things we don't see that someone over in another galaxy would be able to see? Yeah, absolutely. But the idea for our cosmology is like, but statistically, they see the same thing. They'd see about the same number of strongly lensed quasars over their sky as we see over ours. And but they'd be different ones just because of how they line up. Does that make sense?
Yeah,
And does it address your question?
It's not a number, but.
If we had a whiteboard, maybe I could give it a shot as to try to estimate the number density. Yeah, but they are absolutely rare, but we can, if you look deep enough, you tend to be able to see some interesting lensing systems in almost every field. But getting very strongly lensed quasars, for example, is rare. Other questions?
Another question. So actually, a couple of questions
About you said the faster you go, the slower time goes, right?
Yes.
So if you are a photon,
I like where this is going. Yes.
does time exist for the
Nope.
photon?
So time does so the effect gets, again, I used up my quota by far on equations. I think with 3 up there. Is that right? 3? Too many for a public talk. So I'm going to describe this in words. The closer you go to the speed of light, the greater what's called the time dilation factor. That effect becomes infinite as you approach the speed of light. And so the most reasonable way of saying it is time doesn't exist for a photon. There is no rest frame for a photon. which makes sense, right? There's no frame where you could sit in where if you're running fast enough, a photon would appear to be standing still next to you. And that's, if you think about how a clock works, you know, in order, if we're saying like a clock basically has to be something that you can look at while you're standing still. If there's no standing still for a photon, there's no reasonable definition of a photon's time frame.
So is there distance then for photons? Meaning that if a photon has left the sun, come to us, we say it takes a certain amount of time. But from the photon point of view.
So no, and then there's no absolute measure. You basically again have to have sort of a fixed frame of reference. I mean, this is why, you know, in Star Trek, whenever there's these beings of pure energy, it's hard to imagine how they'd organize their society with no clocks or measuring rods.
And then maybe you've answered it already. Why do we say that the speed of light is the absolute?
So why do we say the speed of light is the absolute limit? I mean, so that is a really good question. I mean, I will say in Einstein's special theory of relativity, it's exactly a consequence of all this. So we talked about time, you know, how time works, but there's a number of things that are related to it, right? So, okay, here's a fourth equation because we're in after hours at this point. You guys all learned this F equal, or many of you learned, all of you raised your hand, learned this F equals MA equation in high school or college. That's wrong. It's wrong because, you know, it basically says if you push at a constant force, things will go faster and faster and faster and faster. Einstein gives us a better version of this, which basically says that if you push, if you keep pushing, the momentum goes up and up and up and up, and the speed goes up, but it just approaches the speed of light. So from Einstein's perspective, from the equation perspective, the idea is, why can't you go faster than the speed of light? Because it would take not just an infinite, but I guess technically more than an infinite amount of energy to get you there. That may not be satisfying. Well, what I can say is that having made that prediction, you can then say, oh, this is the absolute speed of light. And somebody who wants to challenge you could be like, I will find something that goes faster than the speed of light. And you may remember a story from, I'm not remembering exactly the year, maybe 6 or 8 years ago, in which a group, I want to say it's CERN, I don't remember exactly where this was, believed that they had discovered faster than light neutrinos. That was the claim. Everybody was like, well, we're skeptical, we're still checking it out, but, and it turned out, you know, and so this would have been a definitive like rebuke to an important part of relativity. I got interviewed by a bunch of places like the Wall Street Journal, in which I was like, no, if that is in fact true, all of relativity is wrong. And it turned out to be like loose cables. I mean, I didn't predict that, but the point is, it really is, it is a, you know, it's one of those things where I could say relativity predicts this, but relativity really does predict this in this case, that all massless particles like go at the speed of light and nothing can go at that speed or faster, period. So great question. Other.
Including gravity waves.
So gravity waves basically are massless, right? So they move at the speed of light. The graviton, if it exists, is massless. It goes at the speed of light. And we call it the speed of light just because light's the most famous one, but it's really the speed of any massless particle. But you know, that's the most well-known one.
I read the path towards quantum gravity has to include time.
I think that's fair.
And that near a black hole, time has to have a number, and that's a question. You just talked about.
So near a black hole, time runs slow. We talked about that. And a theory of quantum. So I'm gonna backtrack a little bit. So normal quantum theories describe things like electromagnetism, right? Ordinary electricity, they describe the nuclear forces, things like that. And they work great. But they basically assume that time runs the same in any given frame of reference. And the problem is that relativity, general relativity, has things like time running slow in strong gravitational fields. And so how do you deal with that? And my answer to you, if that's your question, is yes. No, it is. I mean, it's an incredibly difficult problem because no other theory really addresses that. No other quantum theory really addresses that in that way.
Because at a singularity, you have to somehow factor time,
Yes,
but we don't know how.
we don't know how. We're not particularly close, to be perfectly
We have
honest.
infinities and they keep on canceling out.
Yeah. Well, I mean, those ones they're just infinities, and we sort of say, there's probably some big number where there's a theory we don't know beyond that scale. Other questions?
What do you think of entanglement and speed of light?
So the idea, so quantum entanglement's an interesting idea. I mean, it's not just an idea, it's real. So the idea is that there are quantum systems, for example, that where you've got, you know, the classic example is I create two particles and this one's going to have one spin and this one's going to have another, and you know, one could be up, one could be down. And the idea is if it's totally random and I measure this one as up, then this one is down.
No matter where you are on the universe.
No matter where I am, even if these distance between them is greater than the speed of light. Now, the issue is, you know, and Einstein was sort of skeptical. You didn't like it, spooky action at a distance, that sort of thing.
Mm-hmm.
And the idea, the real problem is you feel like if I measure the spin of this one, I'm making it be spin up or spin down, but the reality is I have no control over it. You wouldn't have a problem with the same sort of thing if I threw two bags over, you know, in each
Or a
direction.
right shoe or a left shoe.
Better than the example I was going to use.
You know, if one is a right, then this one must be a left.
But opening the bag didn't make it right. The difference is that quantum mechanics, you know, it has a random component to it. Okay. I think we have time for like maybe one more if people have it.
So, Mr. Microphone again.
So you showed a chart where you were showing alternate paths for lens light, you know.
Mhm.
So there's a straight path and then there is the just right Goldilocks path and stuff. And,
Yep.
and you use this sort of provocative term, wants to, or likes to go fastest. Or,
Yep,
that's a very loosey-goosey thing.
it is.
What do you mean by that?
So that's a very fair criticism. And you know, it's one of those things where scientists can get in a lot of trouble when they talk that way. Because of course, light has no volition, particles have no volition, right? It's like they don't want to do that. But we can describe physical laws as having like a tendency to minimize certain quantities. So in this particular case, we say, you know, rather than describe every single eventuality, we say a light beam will take a path that, and we would say extremizes the time. And you say, but why? And the answer is because that's the theory. Right? I mean, the theory can be derived from an equation of a slightly lower complexity, but still, like that's the theory. That's the basic idea that comes out of it. That you're basically saying, you know, here are these equations, and you know, again, for those of you who've taken some calculus, it's like then you take a derivative and set it equal to 0. That's the thing we're solving for. And so, you know, when we do that, we're basically saying that is the number that comes out of that equation, is that light will take the path that minimizes the amount of time compared to other nearby paths. That's it. Does it want to? No. It can't want anything because, as we noted before, it has no rest frame.
But
It
it's
can't
not
want or need.
derived from outward from the first principles. It is positive and observed to match, but that doesn't necessarily. You
No,
know,
it's-
like you were talking about the
it-
catenary arc as an example. We know a great deal about
Yeah.
how that works. It is, so how solid is that?
Oh, it's incredibly solid. So the theory, so Einstein's theory I will say this. Einstein's theory has a couple of free parameters in it. One of which is very famous, right? The cosmological constant, right? And Einstein tried to fine tune this cosmological constant to make a static universe, and that was a bit of a mistake. The cosmological constant could, sort of be a repulsive force to basically make the universe not evolve, and it was consistent with the general idea of his theory. That was fine. I mean, that it exists, and it seems to maybe actually exist. I mean, we see something like that cosmologically, but there's another number that comes into it, which is the overall effect of what like you can come up with the principles of relativity, and there's an overall factor that goes into it. And so at the end of the day, in order to actually solve for it, Einstein knew that Newton existed, right? And so there is a number where you basically go through and say, yes, I have to make sure that it predicts the same things as Newton. So the prefactor, basically the overall strength of gravity, the number that goes in front of it, happens to be, and that number in the right units is 8 pi. And it could have been something else, and it would have looked like a very similar theory. It just wouldn't have predicted the same stuff that Newton did. And so it wouldn't have worked at low energies.
Oh, cool. Thank you.
Thanks. And thank you very much. Thank you so much.
Great.
Thank you.
Excellent.
Harold, did you want to say anything?
Yeah.
I think this one. with
Yeah,
respect to
why don't you
black-
come up?
With respect to the black hole, I actually mentioned the book in my last column. Janet Levin's book, How to Survive a Black Hole.
Is really excellent. Three equations is more than I can handle. I was an English major. So, I mean, I heard you said, oh, you all heard that one equation. Everybody's going, yeah. No, I didn't. Never encountered it. But it's excellent. And it talks about that, the feature of, it talks about how answers your question too, about how a photon, there's no time for a photon. And it talks about what happens when you go over the event horizon, which is not particularly a pleasant experience. Only no one will ever know that, hopefully. And it's a small book. It's really little. You can put it in your back pocket, and it's like 150 pages. It even has pictures. So for me, it's really, really good, and it helps explain a lot of those questions. Interstellar is still impossible.
You read books for the pictures.
Yeah, I read books for the picture. Your announcement of meeting said there was something else you were going to cover today. Yes, no?
Was there something else to
I know.
cover tonight?
Don't worry about it. Don't worry about it. So we're back here in October. Thank you so much for coming. I did understand most of it, and that's important. If I'm awake at the end, it's a good sign.
Or somebody nuts you.
Yeah, but thank you for coming. Thanks to those of you who tuned in online. And please remember, we need a treasurer, we need an outreach chair, we need vice presidents, we need an observing chair. Please volunteer. Please let me know, president@dvaa.org. Love to have you aboard. It's a fun group. I mean, if I can be president of astronomy club and I never took physics, come on, seriously, people. But thanks, and we'll see you next month.
All right. Take care, everyone out there.